Let's take a peek at our homework that we had last night. If you remember, last night we were dealing with, or yesterday we were dealing with situations where charged particles were moving through magnetic fields. Charged particle, when it moved through a magnetic field, because it generated its own magnetic field, experienced a magnetic force. We could find the direction of that force by the hand rule for deflection, which said, stick your left thumb or your right thumb in the direction of the particle, fingers in the direction of the field, your palm would automatically point in the direction of the force. We could find the magnitude of that force by using the equation F is equal to QVB. Now, both of those things that I just told you are perfectly valid every time you have a problem in which the particle is moving perpendicular, I should say, to the magnetic field. If it's not moving perpendicular to the magnetic field, the hand rule and this equation are not valid. But the only other situation you'll see if they're not perpendicular is if they're parallel. And if they're parallel, we don't need an equation, we don't need a hand rule. How come? If the particle is moving parallel to the field, the force is what? 0, right. So there's no reason why we'd use an equation or a hand rule to figure out what the direction of the force is or the magnitude of the force is when we know the force is 0. So if it's perpendicular, use the hand rule, use this equation. If it's parallel, there is no force, don't do anything, question's done. If you won't get a question that's not either perpendicular or parallel, some angle other than 0 or 90 degrees. That's why I asked you not to do question number 2B. No, sorry. That was the question yesterday, right, where we had the funny angle. I think it was 30 degrees. I asked you not to do 2B for another reason. We'll talk about that maybe a little bit later today, maybe tomorrow. We have two questions here, 1 and 2A. Any issues with either of those questions? No? All right. Your other bit of homework was worksheet number 11. Let's take a look at worksheet number 11, please. All right, you can see the answers for worksheet number 11 up on the board here now. If there's any questions on worksheet number 11, now would be a great time to ask those questions. Yep. Number 4 and 7 shouldn't be out of the page. It's not what I have. Number 4 should definitely not be out of the page. It should definitely be up. Number 7, no. 4 and 7, no, I see what you're saying here. 4 and 7 should be up. What's the difference between, say, when I say number 7, which is up, and number 8, which is up the page, or toward the top of the page? It's my frame of reference here. Dane? Go ahead. Okay, I'll answer the question in a sec. I thought you were going to answer my question. It's a frame of reference thing. If you look at question number 7, a frame of reference is north, south, east, west, right? So if we go north, south, east, west, and we get the other dimension, right? This is one dimension, this is the other dimension, the third dimension is this way, it's got to be up or down. Okay, if I drive to Calgary, okay, to the north, and then I drive to Banff to the west, and then I want to go in the third dimension, then I've got to climb a ladder and go literally up, not out of the page, right? I'm going up. If one dimension is north, one dimension is west, then the third dimension has got to be up. Page is not my frame of reference. But in question number 8, talks about the alpha particle going into the page, a force to the right of the page. My frame of reference is not north, south, east, west, it's the page. So if my frame of reference is the Earth, north, south, east, west, then up or down is my answer. If my frame of reference is the page, then into or out of the page is my answer. Question 4 and 7, if they were based on the page, then it would be out of the page, yes. Assuming that is, right, that your page is like that, right, as opposed to that. All right, any issues here? Dane, you wanted number 8? Okay, let's take a look at number 8. Number 9 as well. 12. Going once, going twice, 8, 9, and 12. Okay, question number 8 on worksheet number 11 says, an alpha particle traveling into the page experiences a magnetic force to the right of the page. In which direction is the magnetic field? So it's kind of like algebra in the sense on the hand rule. We've got to rearrange the hand rule and solve for a variable that we're not used to solving for. It's usually thumb, fingers, see which way my palm points. This time it's thumb, palm, see which way my fingers point. So the alpha particle is going into the page. Let's go thumb, right thumb, okay, because it's an alpha particle, right thumb into the page. The magnetic force is to the right, so my palm should point to the right. Now, take a look at this, Lorraine. Okay, my fingers right now are pointing toward the top of the page, right? My page. Okay, if you do it on your page, which is horizontal, then it will also be to the top of your page. Does that make sense? But if you do your frame of reference as the Earth, okay, not the page, then my answer is different than your answer, right? I go into the page towards the right. If you said up, right, that's up, right? But on yours, because your page is horizontal, mine's vertical, it would be forward if the frame of reference is the Earth. So if we're using the page as our frame of reference in the question, then our answer has to reflect that. Okay, that makes sense? So thumb, palm, fingers point up, well, or fingers point this, it doesn't really matter. The fingers point toward the top of the page. Is that okay? Dan, is that okay, number 8?
Yeah, I just did it so it's pointing to the right, that's why I got it down.
Okay, so you put the field to the right. So remember that, guys. Thumb, particle, fingers, field, palm, force. Okay, if you've got a force, which we usually don't have, but if you've got it, then you got to make sure that you're looking for the direction of your fingers, not the direction of your palm. Yep. It depends on what the question says. Okay, it all depends on the question. Question number 7 says north, south, east, west. Don't use the page. Question number 8 says alpha particle traveling into the page. Use the page. So it all depends on what the question says. But I will tell you that you won't get if it's a multiple choice question on a test, you won't get one that says option A toward the top of the page, option B up. They'll give you all of the answers relative to whatever it's supposed to be relative to. So it tends to be a little bit easier on the test because of that, because they give you 4 options that are consistent with each other. Okay. All right, number 9 says an alpha particle is traveling at 5 times 10 to the 5 meters per second through a perpendicular magnetic field. What's the magnetic force on the alpha particle? Well, we can't find the direction here, so it really should have said find the magnitude. Why can't we find the direction? We don't know which way they're moving. We know they're perpendicular, so we know the equation applies, but that's about it. The equation is F is equal to QVB. It's an alpha particle, so we look on our data sheet and find the charge of that is 3.2 times 10 to the minus 19. The speed of it is given to me as 5 times 10 to the 5. And the magnetic field is 2 times 10 to the 1. And when we multiply those all together, we end up getting 3.2 times 10 to the minus 12. What was the problem with that one? The charge of the alpha particle? Yeah, you see an alpha particle on your data sheet says 2e. That's 2 times the elementary charge. 2 times 1.6. It gives me 3.2. Did you use the charge of an electron? Okay, that would be the single most common mistake, and I guarantee if this question is on a test, that's one of the options. Okay. 1.6 times 10 to the 12 would be an option, and you pick it, and you think you got it right, but yet it's wrong, so we got to be careful. Next question was number 12. Number 12 says, an alpha particle initially accelerates at a rate of 8.0 times 10 to the 13. What's the, I have something crossed out here in the question. I'm not sure if I changed yours or not. Calculate, oh, that's the problem. That's why you had trouble with number 12, because it should have said calculate the initial force of the alpha particle. No, sorry. I crossed out speed. I put force, and then I crossed out force and solved for speed. So it's right. I'm not sure what I was doing here on my sheet. We're looking for the initial speed here. So we've got the acceleration. Whenever we have the acceleration, whenever we want to find the acceleration, what do we find first? Force, right? And then when you use A is equal to F over m to find acceleration. Well, whenever we have the acceleration, what do you think you're going to do? M times A, and then use some other equation for force, right? So let's get the force, M times A. We can get the value of force, and then we can plug it into this equation. Or you can do what I did, and that is simply set those two equations equal to each other right off the top. Solve for V. V is equal to m times A over Q times B. The mass of the alpha particles on your data sheet, so is the charge, 3.2 times 10 to the minus 19. The magnetic field strength is given to us here, so is the acceleration. We solve for the speed. You get 5.54 times 10 to the 6. So does it matter whether we solve for force and then plug that value in here, or just set the two equal to each other right away? No. They're both exactly the same thing. So whatever tends to work better for you in your mind is what you should do. Is that good? Any more questions on that? All right, done the worksheet. I'd like you to take a look at one multiple choice question, please, number 72. Multiple choice question number 72. And you can submit that as multiple choice question number 1, please. All right, of the responses I've got, guys, 69% of you chose A, 8% of you chose B, 23% of you chose D, and none of you chose C, thus far at least. We've got moving electrons that are deflected by electric fields, gravitational fields, and magnetic fields. It's a good question to help us to kind of see how things are affected by each of these fields. It says one electron is allowed to enter each type of field as shown below. Field 1 is one of the three fields, field 2 is another one, and field 3 is the third one. We want to know what field 1 is, what field 2 is, what field 3 is, if the electron is deflected downwards in each case. The first one I'm going to try to identify is the gravitational field. Why? Why do you think I'm going to identify that one first before anything else, Logan? Yeah, in the end, an electron has mass. If an electron with mass is going to go downwards due to a gravitational field, then the gravitational field has to point downwards. Right? So we're going to identify right away that this is gravity. This gravitational field would cause any particle with mass, including an electron, to be deflected downwards. All right? The next easiest one is the electric field. If I've got a negative particle and I want that negative particle to be deflected downwards, which way do I need the field to be? We saw a couple of courses on our last unit test that are like this, right? Negative particle gets deflected downwards, the field has to be upwards, because the particle gets deflected opposite to the direction of the field. So that would mean field 1 is going to be the electric field. An electric field upward would cause a negative particle to be deflected downwards. That must mean the third one is our magnetic field. Let's just double check it just to make sure. Let's say our left thumb in the direction of the particle, our fingers in the direction of the field, assuming it's magnetic. It's into the page. Palm points downward. Does that magnetic field cause a particle to be deflected downwards? Yes. So that will deflect downwards if that's a magnetic field. We've got electric, magnetic, and gravitational. The answer would be A, which about 70% of you said. Good. Does that make sense for the rest of you? That I made a mistake on that? 23% of you chose D, magnetic, electric, and gravitational. You got these two mixed up. Anybody want to volunteer why you get those two mixed up? How that happened? Or you just weren't sure? You just kind of guessed, kind of. No? Almost a quarter of you said that, but nobody wants to step up? Help out, take one for the team? All right. Let's spend a few minutes now talking about that charged particle in the magnetic field in a little bit more detail. We know that it experiences a force, and we know that force is always perpendicular to its motion. So let's look at what happens to that particle. Not what the value of the force is, we know that now, but rather what happens to it as a result of that force. I'll draw a picture here. A bunch of X's are going to represent my magnetic field. So my magnetic field in this case would be which way? X represents what? Into the page. So my magnetic field in this case would be into the page. Let's say we've got a negative particle entering that magnetic field like this, towards the right. Let's take a look at the direction of the force on that particle. It's moving to the right. It's moving to the right. It will experience a force in which direction? Let's say thumb to the right, fingers into the page, force points down the page. Let's not say down, okay, because our frame of reference is the page here, okay? Okay, let's say down the page here. So there's the force. Let's make F red, and let's make velocity green. Now this particle isn't going to be going to the right anymore, right? It's going to the right, it experiences a force downward. Where's it going to end up going? Somewhere in between, right? So it's going to go down here somewhere. Its velocity is now looking more like this. Which way is the force now? Well, let's go thumb again in the direction of the particle, fingers field, palm points kind of down and to the left, palm points this way. Where's it going to go down? Somewhere in between. So now it's going straight down. Let's find the force. Thumb particle, fingers field, palm points to the left. Magnetic force is to the left. Now where's it going? Going down this way somewhere. Thumb points in the direction of the particle. Fingers points in the direction of the field. Palm points up and to the left. What do you notice about that force in each and every case? Yep. Yes. I'm glad you mentioned the one word. The force is going all in towards the center. In every position, the direction of the magnetic force is toward the center. The center of what? The center of what? Okay, you can't say center, though, without saying the center of what? The center of a square, the center of a triangle, the center of a room, the center of your car, the center of... Yes, yes, it would be the center of a circle. So, there's the first thing that I want you to get from this. The shape of a charged particle's path in a magnetic field will always be a circle. The charged particle is in a circle. The shape of the path is always going to be a circle. Now, we can describe the force acting on this charged particle by the equation that we learned yesterday. F is equal to QVB. Charged particle is moving perpendicular to the field in all of those cases, so the force can be described in all of those cases by that equation, F is equal to QVB. But because the charged particle is going in a circle with the force always toward the center of the circle, we can now also describe the motion of this particle by... What kind of force is it that causes an object to go in a circle? It's called centripetal force. Fc is equal to mv squared over r. So now this equation is also valid. The other one that we learned yesterday is still valid. We're not throwing that out. It's still there. We're still allowed to use it, and we will lots. But now we're also allowed to use F is equal to mv squared over r because that's the shape of the path. Yesterday we just described the force, the value of the force. Now we're describing the actual path. It's a circle, so we have an additional equation that applies. Now, I want to draw your attention to your equation sheet for just a moment, please. Everybody open up your data sheet and try to find that equation, F is equal to mv squared over r, for centripetal force. Tell me where it is on your data sheet. Anybody find that equation on your data sheet? No? Brody? Yes. Yeah, the equation as I've written it isn't on your data sheet. But what is on your data sheet is this. A is equal to v squared over r. That's centripetal acceleration. You're also going to see on your data sheet A is equal to F over m. That's just Newton's second law, the generic equation for force, right? If we combine those, then we're going to get F is equal to mv squared over r, which is exactly the equation that I just showed you can use. Just remember that it in itself is not on your data sheet. You can get it from your data sheet, but you got to put a couple equations together in order to do that. What do you think a pretty common mistake is when you're using this equation, F is equal to mv squared over r? Yep. Forgetting to square the v? Yes. But I'll tell you what a bigger mistake is. Yep. Squaring the r. People seem to want to go mv squared over r squared. You know what I've also seen a lot, believe it or not? People will go 1/2 mv squared over r. Is that the right equation? No. What are they mixing that up with? Kinetic energy. And because a lot of people have done it, I've seen a lot of people do it, it's obviously a fairly easy mistake to make. You know, we get a little careless. It's careless, but it's still an easy mistake to make. So just be careful with that and make sure you use the right one. Two equations that now apply. One, because, well, it's a magnetic force, but two, because that magnetic force causes it to go in a circular path. All right? All of the questions that you saw yesterday on that worksheet, both of these equations applied. We don't need to change the way we solve those questions because we weren't looking for a radius or we weren't looking for anything that required F is equal to mv squared over r. But it was still valid. We just didn't need to use it, which is a good thing because we didn't know that we were allowed to use it yesterday. Now we're going to get some questions where the equation that we used yesterday is still valid, but we're more likely to use the new equation, mv squared over r. If 2 weeks from now you get a question on this, a charged particle moving in a magnetic field, just remember that could be one of the equations, could be the other equation, or it could be some kind of combination of both of them. Maybe we set both of those forces equal to each other. Let's take a look at this example that's not in your book. I'm going to ask you to copy up the question here so that you have it. It says an electron is moving at the speed of 4 times 10 to the 5 to the right through a magnetic field that's directed into the page. Those are perpendicular, right? That means everything we've learned so far is valid. What's the radius of the path of the electron and which direction will it bend? Here's my speed. Here's my magnetic field strength. We've got the charge and the mass of the electron if we look on our data sheet. We want to find r. We have two equations, remember. QVB. And now we have mv squared over r. Which one or ones would you like to use here? Both of them, yes. We're going to use both of them. Now, a lot of you are going to look at this and say, oh, we're looking for radius, so let's use this equation. Great, use this equation. But when you try to use this equation, you're going to realize, trying to solve for r, you don't know what f is. So you know you're going to have to use the other equation to get f. What I do in this question, actually, is combine them. You don't have to. But that tends to be what I do. I say the centripetal force is equal to the magnetic force, or mv squared over r is equal to qvb. You want to do them separately? Go ahead, be my guest. You want to do them together like I am? Doesn't really matter. The one thing about doing it this way is you can actually get rid of one of the v's. Right? Divide both terms by v. One of the v's disappears from both sides, and it saves a little bit of calculations. If you do them separately, then you don't save yourself that work. And you want to solve for r. Let's take the r up by multiplying. And let's take the q and the b down by dividing. I end up getting mv over qb equals r. Or r is equal to 9.11 times 10 to the minus 31 times the speed divided by the charge, which is an electron. People don't usually get the charge of the electron wrong. It's usually the charge of something like an alpha particle that they mess up on, because you get so used to using electrons. But check your data sheet anyways, each and every time to make sure you have the charge and the mass right. The magnetic field is 2.5 times 10 to the minus 2. Now, I don't remember what the answer to this question is, but I'm looking at this, and I do remember that there's a shortcut to solving this one. 1.6 times 2.5 is 4. Therefore, that 4 cancels with those numbers, which leaves me with a radius of 9.11 times 10 to the neg 31 divided by neg 21 would be neg 10. What is it? 5? Oh, sorry, I missed the 5 there. This is 10 to the minus 26 on the top, right? 10 to the minus 26 divided by 10 to the minus 21 gives me 10 to the negative 5. Good. Now, we're not finished yet because we're also looking for the direction that it bends. Which way is it going to bend, up or down? So on that last example that I showed you that it bent downwards, right? Curved downwards. Is this one going to curve downwards or upwards? Well, if the charged particle is going to the right, the magnetic field is into the page, the palm is going to point downwards. Therefore, it's going to curve downwards, just like the example that we showed you a few minutes ago. All right. Oh, would you look at that? Perfect timing, eh? I'd like you to take a look, please, for homework tonight at worksheet number 12. But because it's Halloween, and because we have a kind of a mini test tomorrow, we want to assign all of those questions. There's only 5 of them, I guess. You know what? Let's do 3. Okay, let's just do up to number 3 tomorrow. Prepare for your test. Do up to number 3 for tomorrow, and have a little bit of fun tonight. Go to the movie tonight. Go to movie night at the school tonight. Have a good night, guys.